Okay, hi everyone. I'm sorry for the delay. Thank you very much for joining us at the Topos Colloquium today. We are very happy to have Elaine, Landry, who's going to speak to us about as-if category theory with foundations. And so, Elaine, whenever you're ready, please feel free to share your screen and
All right.
your talk. Thank you.
Thank you. All right, everybody can see the screen?
Yes, I can see
Okay,
that.
good. Okay, excellent. Thank you so much. And thank you so much for the kind invitation. It's a pleasure to be here. I'm just going to give you some context before I get started. So I've been working on foundations and category theory for almost 30 years. And this talk is going to be a talk aimed more at philosophers, but hopefully has some significance for mathematicians. So the view that I put forward was that one should view category theory as a language for mathematical structuralism. And then the philosophical community came back and said, oh, wait, you can't do that because you need some theory that tells you what structures are in this very kind of ontological sense of are. And if you don't do that, then your position is going to reduce to if-thenism. Once I got tenure, I felt a bit free, and I'd always been interested in Plato, so I started working on Plato. For those of you who are interested, there's a book out now on Plato that I just finished. It's also open access, so it's free. You can download it. And as I was working on Plato, I discovered that his view was a lot more intricate and involved than was typically presented. And, you know, in the philosophy of mathematics, we typically have these, you know, on one hand, you either have to be a realist or you're a fictionalist or a nominalist of some type or a formalist. But Plato's view provided us with that middle ground. And so I wrote up my work on Plato and I thought, could one use that position to get at some of these objections and clear the space for the type of position I wanted to argue for? So that's what I'm going to talk about today. So I'm going to do a brief overview of Plato and then just dive into the philosophical debate about using category as a structuralist foundation. All right. So here's my claim that an as-ifist interpretation of mathematics can be used to provide an account of both the practice and applicability of mathematics while avoiding this confusion that I found between mathematical and metaphysical considerations. So I'm first going to begin with Plato to show that much philosophical milk has been spilt owing to our conflating the method of mathematics with the method of philosophy, and then requiring philosophers of mathematics to, you know, answer or be answerable to this method of philosophy when in fact their method is a distinct method. I'm going to use my reading of Plato to develop what I call methodological as-ifism. So that's the view that in mathematics, we treat our hypotheses as if they were first principles, and we do this for the purpose of solving a problem. That's the methodological approach. I'll then extend this as-ifism to modern mathematics, where the method of mathematics becomes what we now call the axiomatic method, noticing that this engenders a shift from as-if hypotheses to as-if axioms, and also engenders a structuralist shift from the investigation of objects themselves to the investigation of objects as a position in a structure. So I'm going to take for granted that the axiomatic method that gets developed in the 18th, 19th, 20th century is really a push towards mathematical structuralism.
Hi, Elaine, I'm sorry. I just want to check, are your slides progressing at this point, or you're still?
No, I'm still on slide 1.
Okay, great. Just wanted to make sure. Thanks.
Okay. Then I'll pause to note that the conflation of the method of mathematics with the method of philosophy is witnessed by the Frege-Hilbert debate and in fact is witnessed by current debates in philosophy of mathematics. So then I'm going to use my methodological as-ifism to reconsider structuralist foundations, and especially the debate between whether one should use set theory or category theory as a foundation. So it's the outline. So here we're now going to start talking about Plato. Plato kept a clear distinction between mathematics and metaphysics, and the knife he used to slice the difference between the two was what he called method. So the mathematical method is supposed to reason down from hypothesis towards a conclusion with the purpose of solving a mathematical problem. Here's what Plato says. The soul is forced to use hypotheses in the investigations of a problem, not traveling up to a first principle, since it cannot escape or get above its hypothesis. The philosophical method reasons up from a hypothesis towards an unhypothetical first principle, and that unhypothetical first principle is supposed to tether that hypothesis by fixing it to a form. Only then can it be used to reason down towards a conclusion with the purpose of solving a philosophical problem. Again, here's what Plato says. Also understand then by the other subsection of the intelligible, that is the philosophical as opposed to the mathematical, I mean what reason itself grasps by the power of dialectical discussion, treating its hypothesis not as first principles, but as genuine hypotheses, that is stepping stones and links in a chain in order to arrive at what is unhypothetical and a first principle of everything. Having grasped this principle, it reverses itself and keeping hold of what follows, comes down to a conclusion, moving through forms, to forms and ending in forms. So it's clear that the dialectical method requires forms. That is, these objects that exist independently of us in a metaphysical realm. However, and this is where people go wrong, the mathematician's method does not require these forms. So the mathematician's hypotheses are taken as if they were first principles, but they are not. The mathematician's objects are taken as if they were stable objects, but they are not. Again, here's what Plato says. Students of geometry, calculation, and the like hypothesize the odd and the even, the various figures, the three kinds of angles, and the other things akin to these in each of their investigations, regarding them as known. These they treat as if they were first principles and do not think it necessary to give an account of them, either to themselves or to others, as if they were evident to everyone, and consistently going from these first principles through the remaining steps, they conclude in full agreement at the point they set out to reach. That is, they solve a problem. So the purpose of the mathematician's method, which begins with taking hypotheses as if they were true first principles, is to solve a mathematical problem. It is not to give a philosophical account of their truth by fixing them to a domain of stable objects, that is, to independently existing forms, or indeed to physical objects. Again, here's what Plato says. Just as in geometry, it's by making use of problems that we will pursue astronomy. We will leave the things in the heavens alone if we are going to participate in astronomy and make the naturally wise element of the soul useful instead of useless. So the utility of mathematics for solving philosophical problems is that it focuses on solving mathematical problems. So thus we come to Plato's methodological, as-ifism. What is that? That is, we treat our hypotheses as if they are true and our objects as if they exist for the purpose of solving a mathematical problem. And here's this method in use. So in solving Meno's mathematical problem, that is the problem that occurs in the Meno, I treat the length of the line that doubles the area of a 2-unit square as if it were a stable object, but it is not. It is only because of the precision of the definitions of square and diagonal that I consistently reason down to the conclusion that the length will be the measure of the diagonal of a 4-unit square. But I cannot know the length of that line itself as a stable object because the length of that line is 2 root 2. So my suggestion here is Plato is specifically choosing this example because he wants to choose an example where we can come to solve a problem without having a stable object. Right? Likewise, in solving the Republic's meta-mathematical problem, so the question in the Republic about mathematics is what all mathematical objects have in common. So here I treat mathematical objects themselves as if they were precisely defined by a geometric theory of proportion. And I do this so I can draw conclusions about their kinship. For example, so I can precisely define numbers themselves as lengths or measures of geometric ratios. But again, I cannot know what numbers themselves are as stable objects. So the hypothetical method of mathematics is distinct from the metaphysical method of philosophy, and as such, so is its ontology and its epistemology. So mathematical objects are objects not of knowledge, but objects of thought. They are real as not as real as philosophical objects, but again, as objects of thought, they are still concerned with being. The mathematical method yields a kind of understanding, but it does not yield knowledge. That is, it yields beliefs that are reliable guides to solving problems because they are born out of precise definitions and their stable method. Only the metaphysical method of philosophy yields true understanding or knowledge, that is, yields true beliefs that are themselves tethered to first principles. So it's only the philosopher's method, the dialectical method, that requires a domain of stable objects, or what Plato calls forms. So against metaphysical realism, what is typically called Platonism, and I'm hoping it won't be for long, mathematics does not need a stable domain of objects, a metaphysics of forms, or a mathematical foundation in that typical sense of a foundation must provide us with objects. It only needs precise definitions and a stable method. So at the object level, mathematical objects are taken at face value as precisely defined by mathematical theories. And at the meta level, mathematical objects themselves as kind of objects are precisely defined by geometric theory of proportion. That's for Plato. So in mathematics, both at the object and the meta level, we treat our hypotheses as if they were true first principles, and consequently our objects as if they exist. And we do this for the purpose of solving mathematical problems. So mathematics as a science here is founded on the precision of its definitions and the stability of the hypothetical method. So the confusion that I want to point out to, and the confusion that I see running through philosophy of mathematics today, is that mathematics is not a science founded on the dialectical method. That is, the truth of its first principles is not to be found by fixing it to a stable domain of objects, be those objects metaphysical objects or foundational objects. So that confusion continues to play out amongst structuralist philosophers of mathematics. So structuralist philosophers of mathematics have continued to conflate the hypothetical method of mathematics with the metaphysical method of philosophy, and so have made structures into objects. They continue to take their background meta-mathematical theories of mathematical structures, that is, what do I have in mind? The structure theory of Shapiro, system theory of Hellman, set theoretic foundationalists, so forth and so on, as metaphysical or as foundational in this metaphysical sense, that is, as providing a domain of stable objects that fix the truth of their axioms. So the correction I want to suggest here is, as with Plato, we should take our background meta-mathematical theory of structure as one, mathematical and not metaphysical, and 2, as providing precise definitions and stable methods, not as providing stable objects. And we should do this so we can act as if our axioms were first principles. And this for the purpose of solving the meta-mathematical problem of how to talk about structures themselves. So my goal here is to say, look, we can use category theory to talk about mathematical structures themselves without turning our talk about structure into talk about objects. So at the object level, mathematical objects are taken as face value, as precisely defined by an axiomatic theory. So a group is an object, is a position in a group structure. That is, it's whatever satisfies the group axioms. At the meta level, mathematical structures themselves as kinds of structures are precisely defined by category theory. That's my foundational claim. So,
Elaine, I'm
yes.
so sorry to disturb again. Are your slides progressing?
Yes.
We're seeing still the first slide, and I'm wondering if
you're seeing
quite a few.
You're
slides.
seeing the first slide.
Yeah, I see your cursor. I see the slide. It says as if mathematics were true, with the
oh my,
blue squares.
It's not okay.
Yeah.
Let's see. Do you now see? What do you see now? The same thing?
I still see the first slide.
Okay, let me exit.
Yeah.
I'm going to exit and start again. I'm really sorry about that.
I'm sorry. I should have talked about this earlier. There were
should have jumped up
the chat
okay.
about this. Yeah.
Okay. Let's see. Okay. So let us go back. Okay. Now, we will screen share again.
I see it now. I see your slides.
Okay.
They're on.
Does it say the Frege-Hilbert debate?
Yes, it does.
Okay.
And
okay, so I
you.
think I left off here. And what I'm going to do is I'm not going to put this in full screen mode because maybe that's part of the problem. So I apologize if it doesn't look as elegant, but okay. So again, the last point here says at a metamathematical level, mathematical structures are taken as kinds of structures, and these are precisely defined by category theory. So again, I take category theory to be a language that allows us to talk about mathematical structures themselves without turning structures into objects. So to provide the detail of these corrections, I'm now going to extend methodological as-ifism to modern mathematics, where, as I said in the beginning, the method of mathematics now shifts from that hypothetical method to the axiomatic method. And this engenders two shifts, and I encourage everyone to look at Burgess's 2015 book, which really provides a nice detailing of this. So the first shift is a shift starting from as-if hypothesis to moving to talking about as-if axioms. That is, starting with taking axioms as if they were true first principles, and a structuralist shift from the investigation of objects themselves to the investigation of objects as positions in a structure. So mathematics as a science is now founded on the stability of the axiomatic method and the precision of its definitions. But now these definitions are implicitly expressed by the axioms themselves. Again, mathematics is not founded on taking axioms as true first principles, and so on the stability of any objects, either mathematical or metaphysical objects. I'm now going to turn to look at the Frege-Hilbert debate and see how this confusion of methods plays out there, and then extend that debate into the current structuralist debate. So Frege, for example, confuses the method of mathematics with the method of philosophy. He takes the method of philosophy to be the method of concept construction. He takes axioms as true first principles and so assumes that we need first a stable domain of objects to fix their truth. For the Phrygian axioms as first principle account, the primitive terms or concepts employed by the axioms must be explicitly defined over a fixed domain of objects before the statement of the axioms. Hilbert, by contrast, takes axioms as if they were true first principles. That is, they implicitly define the primitive terms or concept. So whatever satisfies the axioms is taken as an object that fixes the truth of them. So Hilbert took axioms as implicit definitions over a variable domain, so that axiom systems themselves are but a schema for defining those concepts that organize what we say about objects as variously interpreted. So for Frege, the stability of mathematical definitions and the precision of its method was to be justified by assuming the truth of the axioms, right? So if you're assuming that your axioms are true, something must fix the truth of those axioms. So for arithmetic, those axioms are fixed logically. And for geometry, they're fixed philosophically by Kantian intuition. So Frege's meta-mathematical account of the method of mathematics was, if the axioms are true, then this theorem can be justified. So his focus was on establishing the truth of his axioms. For Hilbert, however, the stability of mathematical definitions and the precision of its method was justified by assuming the consistency as opposed to the truth of the axioms. Hence Hilbert's famous quote, "If the arbitrary postulated axioms do not contradict each other with their collective consequences, then they are true, and the things defined by means of those axioms exist. That, for me, is the criterion of truth and existence." So Hilbert's metamathematical account of the method of mathematics is, if the axioms are consistent, then this theorem can be justified. So his focus was on establishing the consistency of his axioms. Fearing a collapse of formalism, Frege came to reject logical if-thenism as a metamathematical account of the stability of the method of mathematics. Gödel's results likewise collapse Hilbert's logical if-thenist program. What I will now consider is whether, given the structuralist shift from objects themselves to objects as a position in the structure, if these logical if-thenist views can be reconsidered in terms of methodological as opposed to logical, as if as opposed to if-then views that Plato seemed to be offering up. So I'm making two shifts. The first one is a shift from logical considerations to methodological considerations, and then a shift from if-thenism to as-ifism. So, according to Resnick, Frege developed two forms of if-thenism. On the first deductive if-thenist option, mathematics is in the business of establishing results in pure logic. That's the typical view that we have of if-thenism. So this first option can be expressed as A proves T is logically valid, or as the claim that T is derivable from A. On the second structuralist if-thenist option, Frege views a mathematical theory as studying all the properties of structures satisfying certain defining conditions, but he never makes use of the assumption that such structures exist. So here we have a relation of entailment as opposed to a relation of derivability. Resnick next notes that the second option offers us a straightforward path to structuralist accounts of, first, mathematical objects, right? So we see a mathematical object as a position in a structure in the following way. So for example, a natural number is a position in any or all structures satisfying the Dedekind piano-Dedekind axioms, and it offers us a structuralist account of applicability. That is, when one finds a physical structure satisfying the axioms of a theory, the application of that theory is immediate. Now, I don't know that it's immediate, but at least it's in line with this notion of satisfiability. Resnick further mentions a historical virtue that such a structuralist approach is in line with the development of abstract structures like group theory and topology. And here I want to add and category theory. And I also want to add that it's in virtue of the expressive power that category theory has that elevates it to the theory that allows us to best talk about structures themselves. So for 30 years, I've been trying to argue that position, and I've come up against two problems. The first is the structure problem, sometimes known as Hellman's home address problem. And this problem says we need set theory or some other quote unquote foundational theory as a semantic or ontological background meta-mathematical theory of structures themselves. So it's here that Hellman proposes his modal structuralist account of possible concrete structures, and Shapiro offers his Platonist account of actual abstract structures. So it's in attempts to solve these home address problems that Hellman and Shapiro offer up their structuralist accounts. Also, we face the consistency problem. So the first is the vacuity problem, that if-thens are made trivially true by false antecedents. So if we accept structural if-thenism, right, then we have this meta-mathematical if-then, and we all know that if-thens are made trivially true by false antecedents, so that position is untenable. The second problem is that all inconsistent theories will define the same structure. And the final is then one must assume that simply assume that the majority of mathematical theories are consistent. So the objection here is that we're leaving consistency kind of floating. So faced with these problems, Resnick presents us with two meta-mathematical alternatives. We can take the Phrygian route of turning to philosophy and base the assumption of consistency on, quote, a belief in the mathematical reality and so the truth of some theory of structures, which will vouchsafe the consistency of mathematical theories. That's the route that both Shapiro and Hellman take. They hold their theories to be true theories of structure. On the other hand, we can take the Carnapian route of turning to logic and begin with a mathematical theory as a linguistic framework which is referential and thus agrees with the prima facie referential character of mathematical language as used by practicing mathematicians, and argue that since consistency is a mathematical question, it too must be treated logically. So the assertion that a given axiom system is consistent must be construed as conditional upon a background theory with respect to whose truth the deductivist can remain agnostic. So the idea here is, look, let's just get along with relative consistency proofs. However, you hear the philosopher in the back going, oh, but you're going to face an infinite regress if you take that route. You need a true theory that's going to stop that. So let's see how that works out. So Resnick, Shapiro, and Hellman, and most set theoretic foundationalists take the Phrygian metaphysical route. I take the Carnapian, but instead of turning to logical rules in a deductive if-then-ist structure, I turn to mathematical methods in a structural as-ifist context. So I'm going to adopt the strategy of relying on relative consistency proofs, but I'm doing that not in the context of logical rules and what those tell me, but rather mathematical methods. What does that mean? It means that I use category theory as my meta-mathematical background theory for talk of structures themselves as kinds of structures. So for example, the Eilenberg-MacLean axioms talk of object-level structures like groups, topological spaces, deductive systems, you get the idea. The ETCS axioms talk about set structures. And finally, the CCAF axioms for talk about categories themselves. And here I leave the choice of logical rules or methods open. So I'm not presuming that there's one logic, right, that's ranging over the talk of categories themselves. We all know, especially in a categorical setting, right, that different methods are going to require different logics. And I want to allow that to happen. So this meta-mathematical theory is not taken as a metaphysical theory that fixes the truth of axioms by making structures into objects. So this theory is not about objects and arrows. It's not about sets and functions. It's not about categories and functors. Right? There are no structures as objects. So if there are no structures as objects, there's no home address problem. There's no question of, well, where do these objects live? Also, my view is taken as in my view, category theory is taken as a Carnapian linguistic framework. That is, I view mathematics as a language, not as a science. So for me, what category theory provides is not an ontology, right? What it provides is a language that tells us, how do I want to talk about structure? And further, that its axioms are taken as schematic in this Hilbertian sense, that the terms object, arrow, set, function, category, functor are taken as themselves ranging over a variable domain. That is, they're not taken as these Phrygian objects that have a fixed reference. Finally, we act as if category theory were a consistent mathematical theory for the methodological purpose of providing a language for mathematical structuralism. So I would argue there's no consistency problem, right? Because I'm not saying category theory is consistent. I'm saying let's act as if it were consistent for the purpose of providing a foundation for mathematical structuralism. But does that solve the problem? So let's now pause to compare metaphysically interpreted structuralism with methodologically interpreted structuralism to see if we can't finally forestall Shapiro's latest version of the consistency problem, which is aimed exactly at my approach. Namely, that on such a Hilbertian, or what he calls algebraic approach, he says, the possible infinite regress of relative consistency proofs will only be stopped by a true metamathematical theory. Otherwise, we will need to turn to logic and make use of a completeness theorem, or we will need to turn to philosophy and concede that consistency itself is not a logical notion. I take it that's supposed to be a reductio argument. So notice, however, that on my as-if methodological account, to solve the metamathematical problem of possible regress of relative consistency proofs, we need only act as if some theory is true for this metamathematical purpose. So look, if you're worried about the consistency of category theory or of some specific expression of category theory, and you want to give a relative consistency proof of that using set theory, that's great. But that doesn't mean that category theory depends on set theory. It means for the purpose of giving a relative consistency proof, I'm appealing to this other theory, right? So again, let's go back to Hilbert. When he gave his relative consistency proof of geometry in terms of analysis, nobody said, oh, geometry depends on analysis, or analysis provides a foundation. right? No, it was a task. The task was, I want to show that these axioms are consistent or satisfiable. And here's a way to do this. I'm going to rely on this theory to do it. So I act as if that were a stable theory for this purpose. So to think that it needs to be taken, that is this background theory that you use to give your relative consistency proof, to think that such a theory needs to be taken as unconditionally true in either a metaphysical or foundational sense is not only something I remain agnostic about, it's something I outright reject, because it is this move itself that conflates the method of mathematics with the method of philosophy. That is, it's that demand that you require some true theory as a foundation that's getting us into these problems. So the proposed methodological as-ifist position holds that some of our methodological commitments to taking axioms as if they were first principles will be made in light of mathematical practice with the goal of solving mathematical problems. Some will be made in light of mathematical applicability with the goal of solving physical problems. And some will be made in the light of logical or philosophical considerations with the goal of solving metamathematical problems. So it's in this last context that I hold category theory as a foundation. It's the language that best allows us to talk about structures themselves without committing us to the existence of structures. None of these commitments, however, will be made with the goals of solving metaphysical problems. That is, problems about what fixes truth or what fixes consistency. Indeed, there is no fixing truth. There is no fixing consistency in mathematics. So with respect to these logical or philosophical considerations, I'm a pluralist. So does that mean we'll have to call in a logic or a model theory to explain what we mean by satisfaction? Yes. Do we need a meta theory of models themselves? Yes. Does this mean we'll have to take models themselves as objects, that is, as naturalistically constructed, as modally interpreted? No. Does this have to be first order logic? No. Does it have to be classical logic? No. Do we need a meta theory of structures themselves? Yes. Does this mean we'll have to take structures themselves as actually existing or as possibly existing? No. Could this theory be set theory? Yes. Does it have to be set theory? No. Can it be category theory? Yeah. Does it have to be category theory? No. Right? If you're not a mathematical structuralist, right, and your task isn't the question, what is the language that best allows us to talk about structures, then you might not hold category theory as a foundation. So why do I advocate taking category theory as the linguistic framework for mathematical structuralism? So we can give an as-ifist methodological reading of set theory, but it will not be schematic. That is, we'll still have a fixed domain of sets for ZFC, classes for Gödel-Bernays, your elements, as either ontologically or semantically prior. For category theory, the axioms need only be taken as definitionally prior. So just the nature of what it is, right? Set theory, class theories, right? Those require us to take sets or classes or your elements as prior. That's the nature of those theories. And that's why on my reading, they're not great theories for expressing claims we want to make about structure. The second is that category theory takes the objects of mathematics at face value. Because objects and arrows are schematic, or as with MacLean, as we take them as undefined terms or predicates, the structures it talks about, that is sets, groups, topological spaces, you get the idea, can be themselves taken at face value, and so do not require this quote unquote reduction to set theory, right? We're not committed to saying, well, a group really is a set, or a topological space really is a set. No, we just say, well, I have an object, it's a group, right? finally, category theory does better at capturing the shared structure of various kinds of structures in terms of functors, identity maps, categorical equivalents. That is, we need not be merely restricted to isomorphism and the problems that this brings. So again, if we choose to use set theory as our background theory, right, and we want to talk about shared or same structure, we're talking about isomorphism, and we know we have a lot of problems when we do that. So here's my conclusion. When answering the question, wherein lies the meta-mathematical or meta-level conditions for speaking about structures themselves, my question is that, or my answer is that we are methodologically committed to taking category theory axioms as if they were consistent. And it's this move that allows us to methodologically act as if category theory were a foundation for mathematical structuralism. Yet, as with Plato, we all the while realize that metaphysically speaking, it is not a foundation, nor should it be. If we move to that metaphysical shift, we've lost all of the value of taking category theory as a foundation. That's it. Thank you.
Thank you, Elaine. Thank you. That was very a lot of food for thought. So we have quite a bit of time for questions.
Yep.
And I will open up the floor for people. And so if anyone's interested in asking questions, feel free to raise your hand or unmute yourself. And then I will get to you. And I'll also go through the questions in the meeting chat as well. And so maybe if someone has a question, you can go ahead. So I see a question here in the chat from Janet, Janet Singer. So here, the comment was that this is a question for later. I think your phrasing was, there is no fixing truth or consistency in mathematics. That was the quote. There's no fixing truth or consistency in mathematics. And the question is there fixing truth or consistency outside of mathematics?
That's a great question. I think that, so there was a slide back where I said mathematics is not a science, it is a language. And in a previous paper and in an upcoming book, my plan is to argue that it's only in science that our goal is to fix truth. Consistency, I don't know. But I think the goal of science is to fix truth. And more importantly, that it aims to fix truth in just the way that Plato says the philosopher aims to fix truth. That is, it aims to say, look, there's an object that exists independently in the physical world. And my goal is to explain how that object fixes the truth of the statements about that. And then the question is, okay, part of our successful scientific theories make use of mathematics. We've got to know that our mathematical theories are consistent. So consistency still plays a role. But I think the only domains where we fix truth are in science.
Great. Thank you, Elaine.
Yeah. Hi, Janet here. I think you're, if you just embrace the 19th century, Comtean, Peircean view that science never, it only approaches truth asymptotically. It is always relative. That completes the picture. I think your work is great here. I think this is very helpful, and it is a really nice complement to a pragmatic view of the approach to empirical truth. And it's wonderful to hear that this is all derivable from Plato to some extent, and so we're back to the footnotes to Plato situation. Anyway, I'm excited to see this. I think that's very helpful.
Yeah, I do. Just to reply, I do see this as Persian, or at the very least in line with pragmatic approaches to truth, probably more to Hack's view. So Hack has this wonderful kind of combination where she takes pragmatic theories of truth and connects them more to scientific goals. And that's how the aim is to get closer and closer to truth. Yes.
Right. Right. But even Comte, in his positive virtues,
Yes.
said that the positive approach was always, certain, organic, relative, precise, useful, and sympathetic. You know, as you're saying that Plato has been misunderstood, Comte has been grotesquely misunderstood.
Oh, nice. Okay.
So yeah, he said relative truth was all one could ever achieve, and you know, people just misread, took his early work, which was easier to digest, and also John Stuart Mill helped to misdirect people. Comte faced
yeah, freezing.
Yeah, I think Janet, you dropped out. Maybe we wait for a short while.
Just to say too, if anybody drops out or has to go, and you can always email me questions. That's fine too.
So there's I think Mikhail has a question, and I saw that Mikhail, you raised your hand. Would you like to ask your question that you posted in the chat? Okay, I think Mikhail may not be here. So the question, okay, the question from Mikhail was, besides fixing the truth, or called the standard of truth in empirical science, there are other problems like that remain unaddressed, like the adequacy of the language. How do you justify the adequacy of category theory as a language for taking the philosophical problems? So that's the question from Mikhail. How do you justify the adequacy of category theory as a language for taking the philosophical problems?
Yeah, if I understand so for me, right, this is, I guess, an attempt to answer that question, right? So there are various reasons why I prefer category theory, suppose, over set theory, or even homotopy type theory. But I don't know that any of those have to do with the role that it might play in science. Could you read the question again?
Yeah. So the question is, how do you justify the adequacy of category theory as a language for taking, I'm assuming this is taking on philosophical problems?
So for me, I don't know what is meant by a philosophical problem. My task here is to take on the philosophical problem of what's the best language for talking about structures. And I guess my answer is, it is the most expressive language that we have. So again, if we choose to use set theory, we tend to fall back into, you know, this confusion of method and metaphysics, because we have to take sets or classes or your elements as in some sense prior, even if you don't want to take them as ontologically prior, semantically prior. And it's that kind of, I suppose, you know, you could give a schematic reason or a schematic account of sets, but it's not going to be fully expressive. We know that, you know, there's some sense in which you could see, I suppose that's what Bourbaki was trying to do, but we know that they ran into problems with functors. You don't have the same ease of which you can express relationships between various structures in set theory as you do in category theory, I suppose.
Right. Thank you, Elaine. So I have a question of my own.
Sure.
So my background's more in type theory, and one of the things I really liked about type theory is how constructive it is, and to some extent the goal my take home from there is that the goal is often to find a way to construct a concept purely from construction and without having to say, think about introducing too many unnecessary axioms. And so these new concepts show up as maybe new functions or new morphisms that we construct from the others. This is I guess a bit orthogonal to what you're discussing with structures of in category theory, in the sense that I think of category theory as the underlying glue for all these things, and then one extra step we can take further is to try to be constructive about it. I'm just wondering what you think about that. Like, how does this constructivism play in the search for truth or a search for relative truth?
Great question. And that's part of why I think it's really important to be a pluralist. Part of the picture of mathematics that comes up when you have this confusion between this metaphysical method and the mathematical method is we forget that mathematicians are solving various problems, right? And the problem you just asked, which is, how do I construct an object? Right? That's an important question. And if in answering that question, your thought is type theory is the best way to do that, that is in no way orthogonal to this idea. In fact, the idea is to say, look, and that's why I make the distinction between, we have goals that are to do with mathematical practice, and then I see my goal as this more general kind of meta-mathematical. But you're now asking the question for me, which seems to be, there are going to be instances when practice and meta-mathematical considerations kind of come together. And I think that's where the constructivist picture really shines, because it says, if I'm going to use these concepts in my practice, then I have to have some way to have access to them without, So the type of pluralism that I have in mind is exactly the type of picture that would allow for someone to say, I want to use type theory. I want to use a paraconsistent logic. I want to, these are the types of activities that mathematicians and philosophers should be able to take on without, the philosopher going, oh no, you have to use classical logic. Oh no, you should be using set theory. Oh, you should. There aren't shoulds in mathematics, right? There's just tell me your problem and tell me what methods you think are best for solving that problem.
Right. That's good. Thank you.
Yeah.
I think we have time for maybe one or two more questions. I see that Kevin, you raised your hand. Kevin, you'd like to unmute yourself and ask your question?
Sure, thanks. Thanks for the talk. I'm wondering, so I'm pretty convinced by this illustration of a methodological gap between math and the sciences that you're describing in terms of science trying to actually fix a notion of truth in terms of some class of actually existent objects, if I'm saying that fairly. So this seems to open up questions, though. If math is not a science and doesn't fix truth, is it just dumb luck that we find so many actually existing objects that are kind of models of our mathematical theories, and that it helps with science so much?
Great question.
Great question.
Oh, getting feedback. I don't know why. Oh,
Oh, no.
maybe because you both, I think you both are hosting. So if one of you could mute, then I think that's where it's coming from.
Yeah, we've done that. Thanks.
Okay. Yeah. So your question is one that I'm dealing with right now. There's a wonderful quote, you probably know it, by Galileo, that nature's book is written in the language of mathematics. So the question is, why? You know, we have the unreasonable effectiveness of math. I think that just goes too far. I think that if we're going to make our access to what we say about the physical world objective in ways that we can communicate and test and do all of the things that we do in science, then we have to use a language that itself is objective and quantifiable and all of those things. And the fact is that science and mathematics grow up together. I think that it's not, when philosophers pose that question, they seem to think that there was a time at which, you know, physics didn't have mathematics. And there was, like, look at Aristotle, right? So, but when we talk about modern science, what we're talking about is a science that itself is mathematized. Where I think we go wrong in answering that question, and this harkens right back to Plato and his quote about astronomy, what he says about astronomers and cosmologists is that they're looking to the heavens when they should be looking to mathematics. So that the idea is that, yes, of course, astronomy is about things that move in the heavens, but our only way of capturing those motions is mathematics. Now, the first part of the question is also related to, I'm just going to make this claim and then we'll see where we can get to. On my view, a science is such that you have existence first and something is made true in virtue of something existing. And in mathematics, it's the other way around. You have truth, or as if truth, and it's in virtue of something, taking something as if it were true, that you get committed to the stuff. And it's that meet and join that we need to explain, right? So how is it that this language that goes from truth to existence is related to and is applied in a science where we go from existence to truth? So one of the ways I'm attempting to answer that question is by going, this is going to sound very odd, but you know, I've been doing this for 30 years, which was odd, is by going back to Tarski and his initial account of truth. And I had, you know, had taught a grad seminar a couple of years ago, and it was truth, and we talked about Tarski, and there's a paragraph in that initial paper where he says, look, you know, I'm giving you a formal account of truth. In this paper, I've defined truth in terms of satisfiability. And then he has these 3 lines where he says, but if you were talking about a formal system, you could likewise define satisfiability in terms of truth. And I think that's the little gem that one needs to unpack when you offer up an account of how it is that mathematics applies in science.
Cool. Yeah. Thanks a lot for that. At least a little piece of it seems to be almost an anthropic principle where, given that we've been able to say things we all agree on about certain classes of objects that actually exist, we must have had a language capable of saying things that we could all agree on about those objects. But yeah, look forward to seeing where that question goes.
Right. So in the interest of time, I think I'm going to stop the live stream soon. And Elaine, I just wanted to ask if you're okay with sharing your slides for at least
Absolutely.
for slides.
Sure.
And I'll post them on the YouTube site in the comments so people can look at it when they're going through the first part of your talk, which was
Absolutely, yes. And I apologize to everyone for that. I just yeah.
Yeah, my bad for not highlighting this earlier.
Okay.
And,
what's the easiest way to share those is to just put them in.
I think you can email it to me.
Okay.
I'll
And then
post
you put them on YouTube. Yeah, okay, perfect. Perfect.
And, I think typically we stay on after the talk as well. If after I stop the live streaming, if I think I see a few more questions.
Sure.
So,
yeah, no
maybe we
problem.
can continue discussion there. But for now,
Yeah.
let us all thank Elaine again for this wonderful talk. And I'm gonna end the live stream now.
Great.
Okay, yeah, so the live stream is ended. And do you mind if so there are one or two more questions in the chat, maybe I'll
sure.
to you.
Yeah.
So Joe Doyle has a question. He says that when we proceed as if the category theory axioms are true, we still connect them to the rest of mathematics. How do we address the quote recognition problem? i.e., how do we justify saying that the mathematical reasoning we are using correctly fits the category theory axioms? I may look, then he says, I may look at a Rubik's Cube and believe that I can apply group theoretical reasoning to it, but there could be some hidden mechanical lock inside of it in which in fact makes the group theoretical model fail. So let me just ask the question again. How do we justify saying that the mathematical reasoning we're using correctly fits the category CT axioms?
Okay, so if I just want to go back for a little bit. Oh, looks like I can't go back. That's interesting. Can I? Oh yeah, I can. So no. I don't know where it is in my slides, but somewhere I say, for me, the way in which I'm using category theory is to solve a meta-mathematical problem. At the object level, however, you still have, your objects, right? So you have groups, topological spaces, rings, fields, all of the, squares, triangles. And so you don't need category theory at an object level, right? You could say, well, look, I could characterize a group in terms of category theory, but it doesn't. It depends on the problem that you're trying to solve, whether or not you then make an extension and say, oh, I'm going to treat this as a category. A lot of times, we do that in mathematics when we've got, two different types of structures. So suppose we have a topological space and we have a set. That's a good example. And we want to know what's the sense in which they're related, right? We want to look at the maps between those. And then we might need a different concept, right? We might need to bring something like a sheaf in there or something. So that's one way in which category theory helps, because it's got this general language for talking about not just the objects, but all the various relations that one could have between those. And then at the next level, it could say, okay, well, now we could talk about the relations that tend to hold between things like, our objects or our functors. We could talk about identity maps, and we can talk about adjoint functors, and we can talk about universal maps. So that's one way that, but to your question about, Rubik's Cube and group structure, again, my position is kind of problem driven. And so the only way you're going to find out if that Rubik's Cube has a structure of anything other than a group is to keep asking questions about it, keep creating problems. And if one of those problems is a problem that group theory can't solve, then it doesn't have a group structure. And the history of mathematics is kind of replete with these types of examples where, I'm always, when you look at philosophy of mathematics and they'll say, oh, Dedekind was trying to figure out the nature of numbers, and that's why we have the piano-Dedekind axioms. But equally important for him was the abstract structure that number systems themselves had, groups, rings, and fields, and semi-rings, and the relationships between those. And those types of problems are exactly the types of problems that push us in a direction to say, is the structure that I'm, kind of saying is explanatory of this thing the right one? But it's only when we set up problems. Now, in science, some of those problems come from the outside, right? So, just take Newtonian mechanics. Even at the time that it was proposed, they knew it wasn't going to account for the motion of Mercury, right? So that was the thing, that was the problem that still had to be solved. And so what that tells us as what mathematicians do is they solve problems. That's fundamentally what they do. And I think that's a much better and accurate description than saying they look for objects. They solve problems. And it's a better description than saying they look for structures. I don't think mathematicians look for structures. I think philosophers look for structures, because that's a way of speaking about mathematics and what those various activities of problem solving have in common. And that's this idea that we get to one structure and we find out it's related to another, and we want to know why. And I think that's the case of the Rubik's Cube as well, right? We might stop at group structure if it solves the problem, but we might not.
Right. That's very insightful. Thank you. So any more? Yeah, Joe says thanks. Joe Doyle says thanks to your answer. Are there any more questions?
I don't know if you can hear me. This is Lee. I'm on an iPhone, so I'm not sure my speaking tap has worked. Am I?
We can hear you. Yep, we can hear you.
Thanks.
Yeah.
I really appreciated this talk. And to borrow a term, I appreciate the sharp lens that you've placed upon the relationship between mathematics and philosophy. So I'm curious, about your ongoing intellectual interests in applying that same lens to specifically the relationship between mathematics and biology, which many have called the 21st century scientific horizon, and it comes from especially your viewpoint, about language. And my question is, I and certainly not I alone, but there is a community of people often referred to as those interested in biosemiotics, and looking at biology from a linguistic point of view, a semiotic point of view. And so my question is, there is a lot of resistance in science over the centuries to paradigm shifts as being illegitimate in science because they're not scientific. And some of my friends at MIT who are biologists are open to the notion that perhaps the physico-chemical present, thrust in biology is not sufficient, and we need a more semiotic approach. And it seems like someone with your mind for sharp lenses, do you have an interest in kind of wading into that area of kind of the linguistic rejectionism in biology? Does my question make sense, or is it too
Yeah. No, it makes sense. I don't have an interest. I've been taking on the philosophers of physics for a while. But that might be helpful. So, because I suspect that the philosophers of physics have the same kind of view of scientific theories as some of the maybe biologists or philosophers of biology.
Yes.
And so what I said was, there's a group of philosophers of physics called structural realists who are saying, look, even in physics, everything is about structure. We don't need individuals, especially in quantum mechanics. Let's do away with individuals. We're only going to talk about structure. And then I came in and said, okay, wait, you're confusing, a metaphysical use of mathematics with mathematics itself, right? That mathematics is a language that just tells us. So let's take the quantum mechanics case. The use of Lie group structure in quantum mechanics allows us to separate out the different types of particles, right? So it says, boson, fermion, spin, right?
Very nice language.
But it doesn't tell us whether things exist or not, right? I mean,
right.
So what is helpful about my approach is that if people listen, it allows you to really pinpoint what are the questions that are metaphysical questions and what are the questions that are mathematical questions. And you can't go from a mathematical claim to a metaphysical claim. You just can't do it, right? You can't say that the use of group theory in quantum mechanics shows that there are no individuals. But that makes no sense. On the other hand, I think the case of biology is different in the sense that one of the things about biological theories is that they're not heavily mathematized. But you do have, terms that people don't know if they're physical terms or metaphysical terms. If you look at the notion of a gene, you look at the notion, right? But that tells well in favor of, if you see mathematics as a language, then what it's telling you is, here's a term that you should use insofar as it's helpful to solve problems. And if it's not, then don't. But don't be committed to that term as if it was carving nature at its joints just because it's a term. That's a metaphysical use, right? So that's the sense that I would say it might be helpful.
Yes, no, I agree. And your voice would be helpful in avoiding fruitless or worse debates, especially when it comes to emerging revolutions of thought. And so I appreciate your response. Thanks.
Great.
Okay.
We have a raised hand from Mohammed. Would you like to unmute yourself and ask your question?
Yeah, thank you very much. Thank you for the wonderful talk. I have two small questions. One of them is that, unlike, natural numbers, category theory has a finite model. For example, the terminal category. So why are you concerned about consistency? I mean, there is a trivial model like the terminal category. So in which sense are you asking about consistency of a theory that allows finite model or even a trivial model?
Great question. So there's the question of whether we can have a finite model, which clearly we can, right? And so that itself, as you just said, resolve the consistency problem. However, right, what goes into the construction of that are a lot of assumptions about things like size, right? Large categories, small categories, your maps and the allowability of maps. So I think what that shows is, analogy just popped into my head, right? So if you remember Hilbert's program, right? And Hilbert's program goes through if you take primitive recursive arithmetic, right? Again, for the same reasons, you have finite model. But does that really kind of resolve the Gödel results? No, it doesn't, because there's a lot that has to go into the presumptions of that. So I think what an appeal to a finite model tells you is that there's a way to give a model that shows that this is, you know, a consistent theory. But what goes into that might not be the types of concessions that people want to make. Some people want larger categories, right? But I think it serves a purpose, just in the same way that the appeal to primitive recursive arithmetic shows that, look, there's a sense in which Hilbert could have made that work. And again, we're saying there's a sense in which I don't owe you consistency, because I can show you that I can construct this finite model.
Very nice. So the second question is, maybe I misunderstood you when you said that mathematicians solve problems. They do not look for objects, but once they have identified an interesting structure like finite groups, for example, they go and classify them and they look for objects. For example, the monster. The monster is very concrete, and I was educated in Aachen, and people are very interested in finite groups.
Right.
And when I was already studying, they bought 4 gigabyte hard disks to multiply matrices of the monster. So they are really interested in concrete objects.
Yes. So and that is if anything is crucial to the story I want to tell here. It's that objects that appear in mathematics appear to the extent that they're useful to solve problems, right? So as you said, I mean, and that's a history, if I'm right in my interpretation of Plato, Plato wanted to include irrational numbers. And the view of numbers that was available to him at the time was the Pythagorean view of numbers as units, right? As arithmetical units. And his mathematics teacher and Theaetetus were learning from this master that there's another way of viewing numbers, and that was as geometric measures. And they realized that if you looked at numbers as measures, then you could include irrational numbers. So they become objects. And in the same way, look at complex numbers, right? Oh, we need these as roots to solve equations. We don't hear about the things that didn't work, but the things that work very well. And that's what is so interesting about mathematics, is that, I mean, take complex numbers, and then we look at, you know, the role that they play in spherical geometry and points at infinity. But again, it's not that this view doesn't allow in objects, it's that objects get in virtue of their use.
Wonderful, thank you very much.
Yeah.
Okay. I think those are all the questions. And so thank you. Let us thank Elaine one more time for such a wonderful talk and for answering our questions with so much
Of
patience.
course.
Thank you.
Thank you very much. And like I said, if anybody has any further questions, just throw me an email and I'll send you the slides.
Okay. Thank you, everyone.
Perfect.
I'm going to end the Zoom call now. Thanks again.
Okay, thank you.